Betelgeuse, located 642.5 light-years away from Earth, and known as the shoulder of Orion, has always been one of the most fascinating stars in our visible sky. A red supergiant with a surface temperature of about 3,000 Kelvin, millions of years old, and now in the final stage of its evolution. It has spent its lifetime consuming fuel at an extraordinary rate. Recently, its outer layers have behaved erratically. It has dimmed, it has recovered, it has expelled material, and scientists have openly discussed its potential conversion into a supernova. But here is the part that changes everything. Because Betelgeuse is more than 600 light-years away, the light we see today left that star over 6 centuries ago. In simple terms, it is possible that Betelgeuse exploded decades ago, and we would not yet know it. The signal must travel 642.5 years before reaching Earth. That delay transforms a future event into a present uncertainty. And when a red supergiant reaches the end of its life, the result is not subtle. A supernova is the culminating event in a star's existence, an exponential increase in size and temperature followed by an immense release of light and energy. Studies suggest such an explosion can briefly illuminate an entire galaxy. In the case of Betelgeuse, it is estimated that the energy released could exceed everything our sun will emit throughout its entire lifetime. So what would that mean for us? Let's begin with the first and most unsettling element. Betelgeuse sits approximately 642.5 light-years from Earth, a distance so vast that the information we receive from it is fundamentally delayed. Light does not arrive instantly. It must cross hundreds of light-years before being observed and studied on our planet. This means the image of Betelgeuse we see in the night sky is not current. It is historical. What we observe tonight is the star as it was more than 6 centuries ago. The importance of this distance is not only about how far the explosion's effects might reach, but also about when we would know such an explosion had occurred. From our perspective, it is entirely possible that Betelgeuse has already undergone supernova, and we remain unaware simply because the light has not yet completed its journey. That delay creates a unique situation in which the event could be in our past, while still being in our future observationally. Betelgeuse, also known as Alpha Orion due to its classification as a red supergiant, is in the final stage of stellar evolution. Larger stars consume their fuel more rapidly than smaller ones, and Betelgeuse exhausted its hydrogen long ago while expanding in size. Astronomers theorize that it may convert into a Type II supernova and potentially collapse into a neutron star, depending on its oxygen and neon levels. There's also the possibility that it could become a white dwarf. The red coloration of the star results from its relatively low surface temperature of about 3,000 Kelvin, characteristic of red supergiants nearing the end of their life cycle. Its erratic outer activity and brightness variations have fueled ongoing theoretical discussion about its future. The question is not whether Betelgeuse will die. The question is when. And because of the distance involved, our awareness of that moment will always be delayed by centuries. To understand the potential magnitude of a Betelgeuse supernova, the document draws a comparison with the most devastating nuclear events in human history. In 1945, near the end of the Second World War, the United States detonated 2 atomic bombs over Hiroshima and Nagasaki within a span of days. More than 110,000 civilians lost their lives in what remains one of the most tragic episodes in recorded history, and the only 2 instances in which nuclear weapons have been used in a large-scale conflict. Decades later, on April 26, 1986, the Chernobyl nuclear power plant disaster occurred during what was described as a power test gone wrong, leading to the ruin of the surrounding town. These events represent the most impactful nuclear incidents caused by human intervention, and they permanently altered how humanity understands radiation and energy release. Yet, according to the document, second after second across the universe, nuclear-scale explosions occur with even greater magnitude. These events release enough radiation to destroy entire planets in moments. But they occur hundreds of thousands or millions of kilometers away from Earth, far enough that their consequences do not directly affect us. The only consistent source of space radiation influencing our planet is the sun, whose radiation is filtered by the ozone layer. The comparison serves one purpose: to scale our understanding. Human nuclear events are catastrophic at a planetary level, but in the cosmic context, they are minor flashes compared to what stars produce naturally. When a massive star like Betelgeuse reaches the end of its life, it does not fade quietly. A supernova is described as the culminating event of stellar death, in which the star exponentially increases in size and temperature before exploding in an extraordinary release of light and energy. Various studies referenced in the document suggest that the luminosity of such an explosion can briefly illuminate an entire galaxy. In a specific case of Betelgeuse, estimates indicate that its supernova could release more energy than our sun will emit throughout its entire lifetime. Supernovas are therefore classified as the largest explosions known to occur in space. A historical example included in the document is the explosion of the nebula RCW 86 observed by Chinese astronomers in the year 1054. The intensity of that supernova was so extreme that it was clearly visible during daylight hours. That single detail reframes the scale of stellar detonation. If a supernova can outshine the sky during the day from immense cosmic distances, then the explosion of a nearby red supergiant becomes more than an abstract astrophysical event. It becomes a phenomenon with visible, measurable, and historically documented precedent. Compared to Hiroshima, Nagasaki, or Chernobyl, the energy involved is not just greater, it is incomparably greater. For decades, Betelgeuse had been known for its external activity and its periodic fluctuations in brightness. The star would lose part of its luminosity and later recover it over time, a behavior that had been recorded since its discovery. However, in recent years, the behavior of its outer layers became increasingly erratic. Between 2019 and 2021, something unprecedented occurred. The star dimmed dramatically after releasing an immense cloud of material following an explosion. The event deeply unsettled the scientific community. A red supergiant in the final stage of its evolution suddenly losing brightness on that scale was not something that could be ignored, especially given ongoing discussions about its potential conversion into a supernova. The dimming was not subtle. It was observable, measurable, and significant enough to trigger widespread attention among astronomers. Given that Betelgeuse is the closest star of its type to Earth and one of the best subjects available for studying the late stages of stellar evolution, its behavior became a focal point for analysis. The concern was not rooted in speculation, but in direct observation. A star already identified as nearing the end of its life cycle had just exhibited unusual instability. The timing alone intensified the debate surrounding its future. In 2021, scientists determined that the material expelled during the event was traveling at more than 200,000 miles per hour, approximately 320,000 kilometers per hour. Although it was expected that such debris would travel vast distances, the cold of space quickly condensed and suppressed the motion of these particles. This detail was critical. It did not merely explain the dimming. It provided insight into how the mechanics of such stellar expulsions behave in the vacuum of space. The expelled mass formed a cloud that temporarily reduced the visible brightness of the star from Earth, creating the impression that Betelgeuse was fading. At the same time, this event became an invaluable opportunity for modern astrophysics. The ongoing evolution of Betelgeuse has proven to be of enormous scientific value, as it remains the best available subject for analyzing the development and behavior of massive stars in their final stages. Its proximity makes it uniquely observable compared to other red supergiants. The dimming event was therefore both alarming and enlightening. It demonstrated instability consistent with a star nearing supernova. Yet, it also showed that expelled material can behave in ways that limit its long-term expansion due to condensation in the cold of space. The event did not confirm an imminent explosion, but but it reinforced the understanding that Betelgeuse is undergoing significant and measurable change as it approaches the end of its life. If Betelgeuse were to begin its supernova process, the document explains that the initial phase of its conversion could involve an immense release of energy. That release, depending on scale and propagation, could potentially affect electrical networks in parts of the world or even globally in a manner similar to an electromagnetic pulse, commonly referred to as an EMP. The comparison is not presented as certainty, but as a possible consequence tied to the magnitude of stellar energy discharge. Radiation from the explosion could also trigger geomagnetic storms, which in turn could further damage electrical grids, generate unusual visual phenomena in the atmosphere, and alter or decalibrate various satellites, particularly GPS systems. The mechanism described emphasizes radiation interacting with Earth's magnetic and technological systems rather than physical destruction. The concern is not planetary obliteration, but disruption. Electrical infrastructure could experience instability. Satellite-based systems could malfunction. Atmospheric effects could become visible. The chain reaction described remains conditional, but it outlines a technological vulnerability linked to high-energy cosmic events. Even though these probabilities are described as particularly low, the scenario establishes that a supernova of sufficient magnitude is not entirely disconnected from terrestrial systems. It is distant but not irrelevant. Once the red supergiant begins its supernova transformation, Betelgeuse is expected to shine approximately 9 times brighter than the full moon, an event that would be clearly visible from Earth. Scientists preparing for such an occurrence would search for a large influx of neutrinos arriving from the direction of Betelgeuse as an early signal of the explosion. After the initial burst, as the light gradually dims, the remains of the supernova could continue to be visible in the sky for several years. The event would not be momentary. It would linger. While the document states that the likelihood of severe electrical impact remains low, it highlights another certainty: social and cultural upheaval. Humanity has a long-standing tendency to react with fear and alarm when confronted with physical or atmospheric phenomena that lack immediate explanation. The explosion of a red supergiant visible in the night sky, shining brighter than the moon, would inevitably provoke global attention. The event would not only be astronomical, it would be psychological. Public reaction could include fear, speculation, and misunderstanding, particularly among those unaware of the scientific context. For this reason, the document emphasizes knowledge as a crucial virtue, suggesting that understanding such events is essential to counteract unnecessary panic. The explosion, if it occurs within observational range, would be a cosmic spectacle, but its greatest impact may not be physical damage, rather the profound reaction it would trigger across human society. Betelgeuse is not just another star in the sky. It is a red supergiant in the final stage of its evolution. A celestial body that has exhausted its hydrogen, expanded to enormous proportions, and now behaves with increasing irregularity. It has dimmed. It has expelled massive clouds of material. It has reminded astronomers that massive stars do not fade quietly. They end violently. And the most unsettling part is not the explosion itself. It is the delay. At 642.5 light-years away, Betelgeuse exists for us as a historical image. What we observe tonight is the star as it was more than 6 centuries ago. If it exploded decades ago, we would not yet know. The signal would still be traveling. That reality transforms a distant stellar death into an event suspended between past and future, visible only when the light finally completes its journey. If and when that moment arrives, the consequences described are not planetary annihilation, but measurable impact. A burst of energy that could resemble an electromagnetic pulse in effect. Radiation capable of generating geomagnetic storms. Potential disruption to electrical grids and satellite systems. A brightness 9 times stronger than the full moon dominating the sky. A surge of neutrinos arriving first as silent messengers from a dying star, and afterward, a fading light that could remain visible for years. The physical probabilities of severe impact may be low, but the social reaction would not be. History shows that humanity responds with fear to unexplained atmospheric phenomena. A supernova visible to the naked eye, brighter than anything seen in generations, would ignite conversation, speculation, and alarm across the globe. And that is why knowledge matters. Because when that light finally reaches Earth, whether tomorrow or centuries from now, it will not be a surprise to those who understand what they are looking at. It will be the natural culmination of stellar evolution, a process as old as the universe itself. Betelgeuse will eventually die. That is certain. When we see it happen is the only uncertainty. If you want to stay informed about real cosmic events that could reshape how we see the universe, subscribe and activate notifications. Because the next signal that reaches us from deep space may not just be light. It may be history arriving 642 years late. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.